say a few words about Eran. So Eran graduated from the Hebrew University of Jerusalem in 2007. He did his PhD under Gil Kalai, and in fact, all the remaining speakers today will be the descendants of Gil. So Eran spent a few years as a postdoc in Cornell, and then he taught at Ben-Gurion University, and now he's moving to Jerusalem. And let me also mention that Eran just got a very prestigious English prize. So Eran is going to talk about around the g-conjecture.
Thanks, Beth, for the introduction, and thank you for the invitation. And thank you, everybody, for coming, and please feel free to ask questions during the talk. So the g-conjecture is about characterizing the phase numbers in triangulations of spheres, and the around means that we will talk about other stuff as well, which is related to this conjecture. So here's the thing. We start with some background on phase numeration. Then I'll serve the G-theorem for simplicial polytopes and the G-conjecture for spheres. So this part, for those of you who heard Lou's talk last week at Stellenfest, there will be an overlap in this part. But sometimes it's nice to hear again things that we've already heard. Okay, and later we will talk about more general objects, for example, triangulations of manifolds and general polytopes, non-simplicial ones. Later we will move to more special objects, for example, equality cases in the G-theorem, so extremal cases there, and flag spheres. And we will end up with more or less related problems, for example, embedded complexes and cubical polytopes. So let's start by setting some notation for this talk. So delta will stand for a d-1 dimensional finite simplicial complex on n vertices. So this just means a collection of sets which is closed under taking subsets, and it includes all the singletons 1 up to n. So for example, if I have I can, for example, look on a simplicial complex on 4 vertices, 1, 2, 3, 4, and I take all the edges that you see here, those pairs. So this is an example of a simplicial complex. Actually, you see that as I draw it here, I can also think of a simplicial complex as a topological space. You think about those simplexes glued together to form a space. So this will be useful soon. And then I can count how many faces I have in each dimension. So the dimension of a set is one less than its cardinality, because if you think of those as the elements of the set as points, and you think of the affine space, dimension is one less than cardinality. So Fi will stand for the number of faces of cardinality I plus 1, and then we collect all of these numbers together, and this is the F vector. So for example, in this example, we will have F minus 1 stands for the empty set, so it's 1, and then I have F0 is the number of vertices. Here I have 4. And then F1 stands for the number of edges. I have 4, and I don't have faces of higher dimensions, so I just stop here. This is F this square. And sometimes we will write it in polynomial form. It will be convenient. And okay, so a basic result in this area is to characterize the phase numbers of the family of all simplicial complexes. This is due to Suchet-Berger, Ruskal, and Katuna. And yesterday, Kyle told me that it already appears in the work of Macaulay. And the problem we will focus today is to characterize the phase numbers when our simplicial complex is homeomorphic to a sphere of a fixed dimension. So for example, in this case, the boundary of the square is a simplicial complex which is homeomorphic to S1, the one-dimensional sphere. Okay, so that's the problem. So let's warm up with some low dimensions. So if we take the zero-dimensional sphere, just the boundary of a segment, so it has 2 points. So here's the F vector. If I look on triangulation of the one-dimensional sphere, it just amount to taking n bonds, so n vertices, n edges, and I need at least 3 vertices. And if we move on to two-dimensional spheres, so it follows from Euler's formula that if you have vertices and you triangulate your sphere, so you have exactly 2n minus 4 triangles and 3n minus 6 edges. Okay, and here I need at least 4 vertices. Okay, and these are exactly the possible F vectors. Now for 3-dimensional spheres and 4-dimensional spheres, there is also a known characterization, but in higher dimensions it's open. But there is a conjecture what these vectors should be, and now to phrase the conjecture, to be more convenient to encode the information in the phase numbers in an equivalent way by what is called the H numbers. So here you have this polynomial equation to transform from one to the other. So here you express the H numbers in terms of the F number. If you say plug in y equals x minus 1, then you phrase the F numbers in terms of the H numbers. And here it is in polynomial form, the H polynomial. So for example, if we look on this square, then you compute the H vector, it's 1 and 2, 1. So actually this one at the end here, so look what happens. If you plug in into this equation here, x equals 0, so you get that HD is an just alternating sum of the phase number, so it's the up to sign is the reduced Euler characteristic. So if I take a triangulation of a sphere, this is always the same, and because of this correction with the sign here, it's exactly 1. Okay, so for triangulation spheres, always HD is 1. Now you see that I have a 1 here and I have a 1 here, and this is part of then sum of the relations telling you that the H polynomial is a palindrome. Okay, so HI equals HD minus I. In fact, these relations tell you the affine span of all of the F vectors. So these relations are the only linear relations. Okay. But we want to say, okay, so now you see we have this symmetry. So if you want to characterize phase numbers, it's enough to tell what are the possible H0 up to HD over 2. And these numbers we now phrase in terms of what's called the G vector, so we just look on the successive differences. So G0 is set up to be 1, just as H0, but then the next G's are just as successive differences. So the important thing to see is just that to say what are the F vectors, now we are down to saying what are the possible G vectors. Okay, so now what are the possible G vectors? For this we need the notion of an M sequence. So this is just the F vector of an order ideal of monomials. So you have a set of monomials which is closed under divisibility. So for example here we have the xy, so we must have the x and the y and also the 1. These are all the monomials that divide xy. And now we count, in such a collection we just count how many you have in each degree. So we have the 1 is numerical degree 0, so we have 1 of such monomial, then we have x and y, so this is the 2 over there, and then we have those 3 numbers of degree 2, this is the 3 over there. So this is an M sequence, all the sequences that count this object. So just see that if the monomials were all square free, this exactly corresponds to simplicial complexes. So you just identify the elements of the sets with variables. So what can you say about M sequences? So it's a result of Macaulay. He characterized them. So namely, he gave numerical conditions between the elements of the M sequence, characterizing these sequences. So I will not say what are these explicit numerical conditions. What will matter for us is the interpretation of M sequences algebraically, namely the Hilbert series of a standard ring. So you take a polynomial ring modeled out by a homogeneous ideal, and you look on this object as a vector space over the field, and you count what is the dimension in each array. Okay, so and these are also M sequences. Okay, so what is the G? Okay, so now we can state the G theorem. So conjecture by McMullen, which tells us exactly what are the possible phase vectors for boundaries of simplicial polytopes. Polytopes, all of whose faces are just sequences. So the boundary complex is a simplicial complex. So Lou Villela and Carl Lee, they showed one half of the characterization, namely for every M sequence, finite M sequence, they found the appropriate simplicial polytope such that the G of its boundary complex is exactly the M sequence you start with. And the other direction is due to Stanley, also in the same year, 79, to show that whenever you take a boundary of a simplicial polytope, indeed the G vector is an M sequence. Okay, so it's complete characterization. And McMullen's conjecture, he phrased as a question, known as the g-conjecture, is general. This characterization applies to all triangulations of spheres. Okay. So some spheres are not realizable as boundary complexes of simplicial polytopes. So if you have in mind two-dimensional spheres, then actually it is equivalent with that of Stein's, but in higher dimensions you have more spheres. Okay. In particular, to say that the G vector is an M sequence implies that it is non-negative, even this is not known. Just a remark, as we have this symmetry of the H vector, so to say that the G vector is non-negative implies unimodality that we have in previous talk like theta. So, yeah, so it's not known. So now I want to survey Stanley's proof, and the ideas that come into this proof will also play a role in the different scenarios that we will consider later on. So the idea is to associate with your simplicial complex a ring, study algebraic properties of the ring, and then derive combinatorial consequences for the original complex. And this, so the ring is what's called the Stanley-Reisner ring or the phase ring. So fixed and infinite field, consider the polynomial ring with n variables, so n is the number of vertices in our complex. And now mod out by the ideal which is generated by the non-faces of the complex. So for every, in fact, because it's an ideal, it's enough to take the minimal non-faces. So for every minimal non-face of the complex, namely a subset which is not vertices up to n, which is not a face, we associate with it a monomial, just the multiplication of the variable that it corresponds to the elements in that set, and then we just mod out by the ideal that it generates. Okay, so this is the phase ring. So for example, if you are back to our square here, so we need a polynomial ring in 4 variables, and we mod out by the ideal generated by the minimal non-faces. So here are the minimal non-faces. So x1, x3, and x2, x4. Okay, so now we say that this ring is Cohen-Macaulay if you can find generic D elements, degree 1, such that the phase ring is a free module over the ring generated by D. So actually Cohen-Macaulay rings have many different definitions. This is the one that is useful for us now to derive combinatorial consequences. That's what Stanley did. So here is the Hilbert series of the phase rings that we mentioned a few minutes ago. So you see that if you look on so now you look on this phase ring as a vector space over K. As a basis for it, you can take all of the monomials whose support is a face of the complex. So already you see that the Hilbert function a series just depends on the face numbers, and you manipulate it a little bit, and you see that this is the expression. So you have here the H polynomial, which is equivalent to the F vector. In the enumerator, it's a rational function. In the denominator, you have 1 minus d to the d. Now, what does the Cohen-Macaulayness buy us? So we can now look at this at the phase ring as the say. So it's a free module over this ring. So if we now look only as a vector space over K, we can think of it as the tensor of this ring times tensor with the quotient ring. Okay. Now what is the Hilbert series of this ring of K theta? So that's the tensor of k theta 1 tensor with k theta 2, etc. So if we look on polynomial ring with one variable, so what is the Hilbert series? 1 plus t squared plus t. Okay, so it's 1 over 1 minus t. You tensor with d times, so you get this expression here. Okay, so now you just divide and you see that the Hilbert series of this quotient ring is just the H polynomial. In particular, this is a standard ring, so it's we mod out by a homogeneous ideal and then further by another homogeneous ideal. So we get that the H vector is an M sequence. Okay, so all right. So how is it related to our question? So we are interested in triangulations of spheres. Okay. So here's the theorem of Reisner that Cohen-Macaulay-ness is a topological property, namely the phase ring is Cohen-Macaulay if and only if some vanishing homological conditions apply, and in particular these conditions holds for triangulation for spheres. Okay. So now we know that if we have a triangulation of a sphere, the phase ring is Cohen-Macaulay. So the H vector is an M sequence. Okay, so now actually it will be easy to show Stanley's proof of the upper bound conjecture for spheres, saying how big can the phase number be, and the claim that they are bounded by the phase numbers of the cyclic polytope with the same parameters. So it's a specific polytope. I will not get into that. I just want to show you how this algebra now, algebraically you can solve it. So here's the sketch of the proof. So instead of bounding the phase number, let's just show that the H vector is bounded by the H vector of that. This is enough because from the formula we had before, moving from F to H, you see that every phase number is a positive linear combination of the H's. Okay, so that's enough to show that the inequalities for H numbers. Okay, so what is Hi of delta? We've just seen that this is a dimension of the eyepiece of this quotient ring. But this ring is generated by how many generators? So we had, originally we had n generators, but then we mod out by theta 1 up to theta d. So we are left with n minus d generators. So so all the monomials in this generator definitely span the ring, so get this inequality here. And then you just compute that this is the Hi of the specific polytope. Okay. That's the proof. Now let's survey Stanley's proof of the G theorem. So we start with the polytope. So first we can assume that this polytope is an integral one. So so first I want to move the polytope so that the origin is in its interior. Now, because it's simplicial, we can perturb a little bit the vertices to make all of them on rational coordinates, and now we can violate so that they all lie on ZD. Okay, in this situation, you can so now you look on the Fen associated with that, and you can associate this compact complex projective toric variety with your polytope. So for this object, you have the Hard-Lefschetz theorem. So here is this. Okay, for this scenario, we need Stirnick's version. So this tells you that if you look on the cohomology ring of this toric variety, and you so then you can take an element which corresponds to a hyperplane section, and then if you multiply by power of it from degree 2i to the symmetric degree to d minus 2i. So here it's only in even degrees because we took real coefficients, not complex coefficients. Okay, these are isomorphisms. Now, Danilov showed that this homology ring you can interpret as the phase ring. So there is a ring isomorphism from this homology ring to the Stanley-Reisner ring mod by this parameter theta, which halves the degree. Okay, so from this point it's easy to see how to conclude the proof. Let's mod out also by this omega. So because of these isomorphisms, everything above degree d over 2 is now killed. So it's 0. And up to that degree, the half degree, we have, if you just multiply one time from degree I minus 1 to degree I, this is an injection. Okay, so when you mod out, what you get? So you get that the Hilbert series of this quotient is just the G vector. Okay, so two beautiful proofs. And those ideas will also play a role in further development. Okay, so now I want to, any questions for this classic?
Why do you work over the real numbers again? Is it important?
I take a I start with a polytope and I want to use its realization of in RD.
But if you worked over the integers, it would have done? For your the Hilbert series that you did.
Ah. So you want to work over Z rather than over, okay, I think we will need a field here, so when we will take Q, yeah, you can work over Q. Okay, so now let's move to from triangulations of spheres to triangulations of manifolds. Okay, so let delta be an even homology manifold without boundary over the field K. So there is an analog of the dense-Somerville relation to this scenario by Klee. So now the difference between the H numbers is not 0 as we had for the sphere, but it's just a function of the reduced order characteristic. Okay, and now let's look at the phase ring and mode out by those theta 1 up to theta d. So what is the interpretation now? So what is the Hilbert series of this quotient ring? So this is due to Schenzel. So now this ring is not free over theta, so it's not a Cohen-Macaulay ring, it's some relaxation called Buchsbaum ring. And so the result is not the Hilbert series does not correspond to the H numbers, but the correction terms is just a function of the Bethe numbers. Okay, so let's call this expression here the H prime vector. But we really want to be as before, in the scenario before, that we had a phase ring after we modeled by theta, we had that the pieces in the I piece and the D minus I piece were the same dimension, and then we had this hard relation. So we want to imitate that. So Kalai and Novi came up with a further correction to the H prime vector that will yield that. So here's the correction. Okay, so subtract one more expression that depends on Bethe numbers, and if now delta is a connected and orientable manifold, then you play around with Poincaré dualities and then Somerville relations, and you get that the H double prime polynomial is a Paddington. So you get this symmetry here. Okay. So now what would be the best scenario for this? And this is a generalization of Gil-Kalai of the g-conjecture from spheres to manifolds. So the conjecture is that you can find in this quotient ring an ideal that after you mod out by that, you will get a Gornstein ring. So actually the ring being Gornstein already implies that its Hilbert series is symmetric with respect to the middle degree. And we want that after we take this quotient, we want the Hilbert series to be exactly the H double prime vector. And that we will have in this quotient ring, we call it R here, there will be a hard Lefschetz element. So from this, we will be able to conclude that the G double prime is an M sequence. Okay, so that's the conjecture. And so Isabella and H. Schwarz, they found for the first part. So what should we mod out by to get this algebraic interpretation of the H double prime vector? And so in order to explain what they found, so we need to recall what is the circle of an S module. So these are all the elements that are annihilated by the maximal ideal. Okay, so the ideal that is needed here is the following. You take the circle up to degree d minus 1. So except for the top degree. There it's already one dimensional. You want to keep it this way. It's already one dimensional here before you take it. Okay, after you mod out by that, you get a quotient ring of Gornstein, and its Hilbert series is exactly the H double prime. In order to prove it, so just some hints to the proof, so they computed the circle in terms of local cohomology modules of the phase ring. And these you can compute by Hofstadter formula using simplicial homology of phase rings. Okay. Can we say more about the phase vectors of the manifold? And here is maybe what is the correct G vector for this scenario. So you need to have a further correction here. You struck by another function of the Betti numbers. And so together with Satoshi Mwai, Satoshi is here, we show the following. So now assume that all the vertex links of the delta are polytopic. This assumption is just to ensure us the hard links, that we can apply hard Lifshitz for face links. And in fact, you don't need all of the hard Lifshitz, just need the weaker weak Lifshitz property. So anyhow, the assumption is just to let us use that algebraic property. So then you can find in an ideal in the ring from before, so that you mod out by that, you get that this G double prime vector is a Hilbert series. So in particular, it is an M sequence, it's non-negative, so the non-negativity of this G tilde is stronger than the non-negativity of G double prime, because we have this extra correction. Okay. Now let's switch to another generalization. So instead of moving from spheres to manifold, we will move from spheres to what's called doubly Cohen-Macaulay complexes. And the definition is that you take a Cohen-Macaulay complex such that after you remove any vertex, what you get is again a Cohen-Macaulay complex of the same dimension. Examples are, for example, spheres. If you remove a point from a sphere, the link of a vertex from a sphere, what you are left with is a ball, which is again Cohen-Macaulay by Riesner's theorem. We gave this topological condition. So spheres are examples, geometric lattices are examples, and even more general complexes with a ear decomposition. So suppose you start with a sphere, and now you glue ears onto the sphere. So an ear is, again, so for what you already had before, you just glue ear. Every ear is a ball such that its boundary is just embedded in what you already had. So for graphs, it just means to be two connected. Okay, so Walker showed that the two Cohen-Macaulayness is a topological property. So apart from the conditions for Cohen-Macaulayness, you also need this extra condition here, this one. And then Bjorner and Schwarz conjecture that for two Cohen-Macaulay complexes, also the G vector is an M sequence. Right? Here the H vector actually is not symmetric. But the conjecture is that the G vector, when you just take differences up to the middle, is still an M sequence, particular non-negative, which is also okay. So I could show that up to G2 it's correct. So in particular G2 is non-negative, and all of this initial part is an M sequence. And the idea follows Calais' proof of Barnett's lower bound theorem for simplicial polytopes, which uses framework rigidity. So I want to tell you a little bit about framework rigidity. So to say that the graph, so it's about the graph. So the whole claim is just about, look, up to G2 we just said we are concerned only with vertices and edges of our complex. So we can just consider the one skeleton of the graph of the complex. So we say that the graph is d-rigid. It's the following hand. So take a generic embedding of the vertices into R to the D. Whenever you have an edge in the graph, put an iron rod. Okay? Another question is, can you perturb the vertices a little bit such that the edge lengths are preserved? Okay, of course you can do it, just move it a little bit. Rotate it a little bit. But can you do it in a way that doesn't come from an isometry of the space? If you cannot do it, you say it's d-rigid. If you can do it, you say it's flexible. So for example, okay, let's look on this square in R2. So you see that I can move a little bit like that, these edges, so it's not rigid. This does not come from it, this is fixed. But if I will put here this extra edge, this rigidifies the thing. Okay, so why is it relevant? So to detect rigidity, you look on the rank of what's called the rigidity matrix. So if you have here the map from the vertices to R to the D, you look on the matrix where if you have an edge VU, and you look now on the column that corresponds to VU, you put here phi V minus phi U, and here for the, so here you have D rows, and D rows. And for the D rows of U, you put phi U minus phi V, and in the rest of the column, you put zeros. So that's the rigidity matrix. And the question is whether its rank achieves the rank that you would get if you had a complete graph course, you cannot go beyond that. Okay. Okay. And the rank there is dn minus d plus 1 choose 2. Okay, so if you achieve this degree, you are rigid. So this already tells you the non-negativity of G2, because non-negativity of G2 just amounts to saying that the number of edges is at least that much. So of course, if this is the degree, and the number of columns you have is just the number of edges, okay, this already gives that. To show the other part that it's a Macaulay sequence, we need a result of Carly that shows that the rigidity is equivalent to the following, that in the face ring, if you look on the, after you model the theta, you look on the map from the degree 1 to the same thing at degree 2 by multiplication by omega, you need this to be an injection. Okay, this is equivalent, so you get the edge. Okay, and Athanasiadis and Becker find a joint generalization for two Cohen-Macaulay complexes and triangulations of manifolds, what they call Buchsbaum-Starr complexes. So this seems to be the right generalization of those two words, and the conjecture there, a similar picture. So, I mean, they show that up to G2 you have an M sequence, but the conjecture is a similar thing we saw for manifolds. Which implies that the G double prime vector for those is going to be an M sequence. So this is kind of the most optimistic conjecture, generalization of the G conjecture for in that generality. Okay. In a different way to generalize is to move from simplicial polytopes, where we have the G theorem, to general polytopes. Okay, so here the toric, Stanley defined the toric G and the toric H in the following way. So it's by some recurrence. So again, the G is defined by successive differences of the H, but here the H is defined by the following recurrence. So you compute the G for proper faces, multiply them by the correct weight, and that is the definition. So the reason to do this definition is because this recurrence holds for the Goreski-Merfixon intersection, McPherson intersection homology for rational polytopes. We'll get back to that soon. And then Stanley showed that indeed with this definition, the H vector is symmetric, and the H and the G, in the case when you specialize to simplicial polytopes, it recovers the original definition. Okay, so, and he conjectures that also here the toric G vector is an M sequence for all polytopes, and even more generally for polyhedral spheres and more. Polyhedral sphere, I mean just you have every face is a polytope and you glue them together along the faces. Okay, so Carew proved, this was a major breakthrough, that the toric G vector is indeed non-negative, and the tool he used is to prove a Hard-Lefschetz theorem for what is called the combinatorial intersection homology of a polytope. This was developed by various groups of researchers, and the point there is to generalize the intersection homology for rational polytopes to general polytopes. So maybe first of all you can wonder, why do we need this? So indeed there are polytopes that you cannot realize with rational coordinates. You cannot place all of the vertices in the rational coordinates. So this was, examples like that were first found by Michapeles. And now, I don't know, a problem, I don't know if it's a problem, it's just it's a fact of life that this combinatorial intersection homology also, the intersection homology, it's not a ring. It's just a module over R theta. So we get the non-negativity, but we cannot conclude that it's an M sequence as before. This is still open. To show that, okay, this question is still open. Now, if you go a bit beyond polytopes to polyhedral sphere, we already don't know anything. So like the most simple thing you can think of is you take a three-dimensional sphere. So for two dimensions, it's very easy. You can do it. But if you take three-dimensional sphere, polyhedral one, now there is no fan that you can use, so you cannot start even the construction of the intersection homology. And even we don't know the G2 is non-negative. So right, the most basic question we don't know in this scenario. Okay. And now let's move to more special cases. So first is about the equality extremal cases in the G theorem. So the generalized Loban conjecture by McMullen and Walkup say that if you have a boundary of simplicial polytope, the G vector is non-negative. This by now we know. It's even though it's an M sequence, that still is true. And further, that if some G entry is 0, this can happen if and only if the polytope is what's called K-1 state. So let me explain this. So take any, you have a polytope and now you want to triangulate it. But you don't want to add too many new faces. So first of all, you don't add, so if you can always triangulate a polytope without new vertices. Just by adding edges and higher dimensional faces, you can always triangulate. It's an easy exercise. But can you do it even without new edges, without new triangles? So the stackness is about that. So for the polytope to be K-1 stack means that you can triangulate it with no new faces of low dimension. So all the new faces in the triangulation must have dimension more than D minus K, in particular above half the dimension. So this gives a severe restrictions on the stackness. For example, if we take K equals 2, so this was proved by Kalai this case, okay, say K equals 2, then the stacked polytopes are, you obtain them in the following way. You take a simplex, and now you pick a face and stack a pyramid over that face. And then you pick another face and stack a pyramid over that. And if you do it carefully, you preserve polytope value. And these are the only ones. There are no more polytopes with G2 equals 0. Okay, so McMullen and Walkup show that indeed K-1 stackness implies the vanishing of GK. Kalai did the K equals 2 case. Now about the other implications. Suppose now that GK equals 0, we want to show stackness. So McMullen showed that if the conjecture is true, there's only one way how to triangulate this polytope. And recently, Bagchi and Data also said what it should be, this triangulation. So here I wrote what it should be, and now I'll just try to explain it. So you are not allowed to put faces of dimension D minus K or less. So what we will do, we will put in all of the other ones. All of the ones that we could potentially put in, we will put in. Namely, all the faces whose D minus 1 skeleton is already in the boundary of your polytope, we will put them in. So it's like the maximal triangulation that is allowed with this restriction of A instead. Okay, and together with Satoshi, we prove that indeed this works. This indeed triangulates the polytope. So here, I will fit again this to the theorem. So let me just give you a few ingredients from the proof. So first one is geometric. First, you show that if you take the convex hulls of all of these faces that we just put in, these together, this is an embedding of this complex in the polytope. But what we need to show is that it's the whole polytope. Maybe there are some gaps, some points in between that are not covered by these convex hulls. Okay, so now there is a topological ingredient. You can use Alexander duality to show that if it's not everything, then the D minus 1 homology of this complex will not be 0. Okay? So now I want to show that it is 0. And the way to show it now is an algebra. The algebraic proof of the part of the proof is we use the Hard-Lefschetz theorem and the GK is 0 to show that indeed this complex is Cohen-Macaulay of dimension D. In particular, by Riesner's theorem, it means that the D plus minus 1 homology vanishes. Okay? So actually the algebraic part is the heart of the proof, and to show the Cohen-Macaulayness, we need just some ingredients. So results of Kalai and Nagel show you that in our scenario you don't have you don't have minimal non-faces in a certain range of dimensions, and then we need Green's crystallization principle to conclude the proof. So actually, to show the Cohen-Macaulay'ness of this complex, we show Cohen-Macaulay'ness of the generic initial ideal that correspond to this complex. That implies. Okay, maybe it's enough about just to get a flavor of what gets into the proof. Now another special case. Now let's move from general simplicial spheres to flag spheres. So a complex is flag if all of its minimal non-faces have size 2. Okay, so for example, if you take the boundary of the octahedron or icosahedron, these are examples of flag two-dimensional spheres. And in fact, saying that the complex is flag, this gives no topological restriction, because take any simplicial complex, if you take its barycentric subdivision, you preserve the topological type, and it becomes flat. Okay, so there are many examples, and so it seems that for these you can maybe stronger generalize the Laurent conjecture can be phrased. Not only that the G vector is non-negative, but what's called the gamma vector is non-negative. So we look now, we have our flag sphere, we look on its H vector, and we now, so we know it's a palindrome, and we want to express it now in a new basis. And the basis is 1 plus t to the d, t times 1 plus t to the d minus 2, etc. The coefficients with respect to this basis are what's called the gamma vector. So for example, if you take octahedral sphere, the gamma vector is just 1, and this is the minimizer of the phase numbers among all flag spheres. Okay, to say if the Gall's conjectures say that the gamma vector is always non-negative, and it's here that gamma 0 is always 1, so in particular, what I just mentioned here about minimization of gamma by the octahedral sphere would be a sort of corollary from Gall's conjecture. Anyhow, like we don't know that the G vector is non-negative, we also don't know that the gamma vector is non-negative. So it's also a wide open conjecture. And where could it come from? So for the G we have a candidate. We know that if we will prove this hard-Lefschetz property, we will have an algebraic interpretation. For the gamma, we still don't know what it should stand for. But here is some direction. So here is again Gall's conjecture. So all Gall knows, maybe that's why he came up with this. So if you look on the top coefficient of the gamma vector, its non-negativity is equivalent to what the Charney-Davis conjecture. Gall proved that it is indeed non-negative for spheres up to dimension 4. This is based on results by Davis and Okun. And together with Kai, so Kai is also here, just trying to think what this gamma could stand for. So we have this conjecture that if you have a flat sphere, its gamma vector is the F vector of some simplicial complex, and even more balanced simplicial complex. Let's say more a bit. We'll get back to balanced complexes soon. So anyhow, we show that it's true for Hofstad complexes, and together with Brigitte, we show that it's true for barycentric subdivision. And H-bet and independently Volodin show that it's true for the spheres that you obtain in the following way. You start with the octahedral one, just 2 points suspension, 2 points, etc. many times. And now you start with that, and now you repeat subdividing edges. So it's true. In this context, it's easy to show that the gamma vector is non-negative, but it's not so easy to show that it's the F vector of even a flag complex, which is stronger than the assertion here. And okay, maybe at first sight this family may look a bit artificial, but anyhow it includes, for example, all flagness tohedra, that were studied by many people, some of them are here, sitting here now. Okay, so for example, the associahedron, the permutahedron, there are examples. Okay, now I want to switch to more or less related problems. So first let's talk about embedded complexes. So it's a classical result if you have a planar graph, if the number of edges is at most 3n minus 6. That already goes back to Descartes, it follows from Euler's formula. Now what is the generalization in higher dimension? So here is a question, a problem raised by Urbach. Can you find a constant depending on D such that whenever you have a d minus 1 dimensional complex and that embeds in the sphere twice its dimension, is it true that the number of d minus 1 faces is at most constant, is constant times the number of d minus 2 faces? So for the case d equals 2, we see here case d equals 2, we see that C2 equals 3 points. Okay? But in higher dimension it's open, we don't know. So to approach this conjecture, so first let's look on the floors complex. So you take 2d plus 1 vertices and all of the d minus 1 dimensional faces among them, and this induces a complex. For example, if you take 5 vertices and all of the pairs, you get K5. It's not planar, and in general, this complex does not embed in twice its dimension. This follows as a result of Van Kampen and floors. You can use Van Kampen obstruction to prove it. It's some characteristic class in the cohomology ring of the deleted product or deleted joint associated with your original simplification complex. It's not specified more, but that's what you need that to, okay, you can use that to prove this. And the Kalai-Sarkar conjecture that if your complex embeds in a sphere of that dimension, then its symmetric shifting, which does not contain this as the floors complex as a subcomplex. So the symmetric shifting, let's not get to exact definition, but it just, you use the face ring, you do some generic initializing process, etc. You get a new complex with the same face numbers, but it has some advantages. Combinatorially, it's simpler. And anyhow, if this conjecture is true, then it gives you tight bound in Grunbaum conjecture, where CD is d plus 1, and it will also prove the g-conjecture, for at least for piecewise linear spheres. And for this, you need another unpublished work by H. Barth. Okay, so here's again the Kalai-Sarkar conjecture. So now, how would you prove something like this? So maybe one approach is to see, okay, let's say that if delta embeds, then maybe also delta S embeds. If delta S embeds, then it cannot contain this complex, and we are done. That's a natural approach, only that it's false. Even if you take graphs, planar graphs, you shift them, later you can find K33. Okay? You cannot find K5, but you can find K33. So to get around it in a project together with Bella and Gil Kalai, we try the following. So instead of considering any complex, you can assume that it is balanced. Namely, you can color its vertices by D color so that every face is rainbow. So all of the vertices get different colors. Because if you use random coloring, you can see that you can take a subcomplex which contains a fraction of the original top dimensional faces. So we just, if in Grunbaum conjecture we just needed some constant, not a sharp constant, then it's safe to look at balanced complexes. And here, instead of floors complex, we will look on another complex that doesn't embed in twice its dimension. This is called the Van Kampen complex. We take 3 points, join with 3 points, join with 3 points, etc. until you get to d minus 1 dimension. So for example, if you do it 2 times, it's just K33, which is non-planar. Okay, that's an example. So here is the conjecture. If your balanced complex embeds in a sphere twice its dimension, then in its balance shifting, so it's some variation on symmetric shifting by Bella and Eric Baxon, then you cannot find there this Van Kampen complex. If this conjecture is true, then you get Grunbaum's conjecture that with the worst constant, and we show that it's true at least for bipartite graphs. So, okay, first step. Anyhow, the advantage here, so why don't we want to work with the Kalai? Remember why we didn't want to work with Kalai-Sarkar conjecture to start with. So the advantage in this conjecture is that not finding the Van Kampen complex in the balance shifting is equivalent to embeddability of the shifted complex. So now the natural approach you can use it. So at least it's equivalent to original conjecture. So you need to show that if delta embeds in the sphere, then its balance shifting embeds in the sphere. Okay, that's the approach. Okay, I wanted also to tell you about cubical complexes, but So in cubical, so we have the definition of simplicial complex. Just delete simplex, put cube, and you get it. So but you need combinatorial cubes. So you take combinatorial cubes and you glue them together along a phase, a common phase. So intersection of each two is a common phase. So for cubical complex polytopes, Jokush conjecture the Lobar has a Lobar conjecture that if you take a cubical dipolytope, at least three-dimensional, the number of edges is at least that much, and this is achieved by stacked cubical polytopes. You start with a cube, you pick a facet, you stack a cube on that facet. You pick another facet, you stack a cube. Again, if you are careful, you will get a polytope. Right? If you don't, it's not a polytope. But anyhow, you can also conjecture it for cubical spheres, but we don't care about that. So Ronadin introduced an analog of the G vector to cubical polytopes. And the Jokush conjecture is just to say that the cubical G2 is non-negative. Beforehand, we proved using a framework rigidity. Now, for the cubical G2, so this was for the usual G2. For the cubical G2, there's still we don't know an algebraic meaning for it. And with a new project with Bella and Hill, we introduced what we call bipartite rigidity. So it's some variant of framework rigidity to bipartite graph. That, I didn't say, but if you have a cubical polytope, the graph is bipartite. Okay, otherwise everything. Okay, so it's also a nice exercise. The graph cubical polytope is bipartite. So this is and so at least we have with this new theory, we have a conjecture that may give algebraic interpretation to the cubical G2, but it's also open. And that's it.
Okay, we have time for about 3 short questions. Any questions?